Okay, and this is what we had started. So angle of depth gives the direction of the Earth's magnetic field in the vertical plane. So let us say, let's continue from yesterday. Let us say the ship is here, okay, and the direction of the Earth's magnetic field is this, and this is the horizontal. Horizontal. So then this angle is called angle of depth. Okay. This angle is called the angle of depth. So angle of depth we can define as it is a vertical angle which the direction of the Earth's magnetic field makes with the horizontal at that place. Okay. Now angle of depth can be positive. So positive and negative is just a sign convention. Just because somebody decided to call it this way, that is why we are doing it this way. So angle of depth will be called positive if a red end of the needle, a red end of needle is below horizontal. So if we look at this magnetic compass needle, so because it is the north end of the needle which is pointing towards this, so here the red end of the needle is below horizontal, correct? And if you look at the other end of the needle, other end of the needle will be like this, correct? This is the blue end. Blue end means south end. So we draw the horizontal like this. So this is also angle of depth, and this is also angle of depth. But blue end of the needle is above the horizontal, you can see, and the red end of the needle is below the horizontal. So if red end of the needle is below the horizontal, then we call it the angle of depth as positive. And of course, if the blue end is, if the red end is above the horizontal, so negative it will be called. If it is, same thing is above horizontal. So that will be, let's say you're on the southern hemisphere. In the southern hemisphere, which end of the needle will be pointing in the direction? It is the blue end. And this is the horizontal.
सर
Yes.
हाँ सर, बोर्ड का लिखा हुआ क्लियर नहीं दिख रहा है सर, कुछ क्लियर नहीं दिख रहा है, क्लियर नहीं दिख रहा है।
क्लियर नहीं दिख रहा है?
यस सर, क्लियर नहीं दिख रहा है।
यस सर, क्लियर नहीं दिख रहा है थोड़ा।
अच्छा एक मिनट, जस्ट होल्ड ऑन। Okay, can you see now? Clear? Hello.
Yes, sir. Now clear. Now clear.
Okay, is the full board visible?
Yes, sir. Now full board is visible.
Okay. Okay. So if the now the blue end of the needle will be pointing towards this. Okay. So in this case, what will happen to the red end? Red end will be pointing like this. Okay. So in the red end of the needle is now above horizontal. So here the dip of angle is it is negative here, and it is positive. So we can say that angle of dip will be positive in the northern hemisphere, and angle of dip will be negative in the southern hemisphere. So if we talk about the angle of dip, what will be the angle of dip at equator? What will be the angle of dip at equator? Hello?
Sir, 0, sir.
Correct. So angle of dip at equator will be 0 because the direction of the Earth's magnetic field is horizontal at equator. So what angle it will make with the horizontal? 0. What will be the angle of dip at poles?
Ninety
90.
degree.
90. Okay. So angle of dip at poles will be 90 because the direction of the Earth's magnetic field is vertical. So anything vertical, what angle it will make with the horizontal? 90. Okay. And as we go from the equator towards the pole, the angle of dip will continue to increase. So like we are sitting in latitude of about approximately, let's say in Mumbai in 23 degrees. So the angle of dip may be 17, 18 degrees. As we continue going towards north latitudes, okay, the angle of dip will continue to increase. Starting from 0 at equator to poles at 90. Okay. So the angle of dip values are also tabulated, okay, for different places of the world. It is available in the chart also. It is also available in the tabular form. Okay. So angle of dip is actually found out by one instrument which is called dip circle, but that is not there in your syllabus. But anyway, for finding out the angle of dip, what is the equipment which is used? Dip circle. Okay, third thing what we have. So first was magnetic variation, second is angle of dip. So these two define the direction. This one is defining the direction in the horizontal plane, this one in the vertical plane. So that direction has been defined. How the direction was defined? Let us say the place where you are sitting. Suppose I say that variation is 5 degrees east and the angle of dip is plus 25. You know the direction because the place where you are sitting, you know the direction of the north, geographical north. So from there, 5 degrees towards east is the direction of the Earth's magnetic field in the horizontal plane. Then you know that angle of dip is 20 degrees. So you make an angle of 20 degrees with the horizontal. So that will become your direction of the Earth's magnetic field. There is one diagram which is good for showing the both things in one diagram. Let me try to make that thing. Let's say Okay. So let us say this is the let us say magnetic meridian, and this one is what? Your geographical meridian. Okay. So the angle between the two, this angle is your variation. This angle. एक meridian ऐसे, एक meridian ऐसे. So the angle between them is. And let us say if I suspend a magnetic needle here, and that needle is suspended like this, and let us say that needle is pointing in this direction. Okay, so the needle will always point in the direction of the field. So let us say the direction of the field here is like this, and let us say this is horizontal. Okay, so if this is the horizontal, and then this is your angle of dip. So a freely suspended magnetic needle is pointing in this direction, so the needle will always point in the direction of the magnetic field. So this is the direction of the field, and this is the horizontal. So this is the angle of dip. Okay. Hello.
Okay, sir.
And as you can see, this angle of dip is an angle which is forming in what plane? It is forming in the plane of It is forming in the plane of magnetic meridian. So actually, that is also should be included in the definition, but that's okay. The third one is called, the third element is called magnetic field strength. Magnetic field strength. So now we have talked about the direction. Let us talk about the magnitude. So what will be the magnetic field strength of the Earth's magnetic field at any point on the surface of the Earth? So we can take the same definition, the definition what we have used in the case of general definition of the magnetic field strength. The magnetic field strength can be defined as the magnetic field strength at any point on the surface of the Earth can be defined as the force acting on the unit north pole acting at that point. So let us say this is the Earth, and I want to know that what is the direction. What is the magnetic field strength of the Earth at this point? So what we do, I keep a unit north pole here. So whatever is the force acting on this unit north pole due to the Earth magnetism, that is what is the magnetic field strength. Okay. The magnetic field strength at any point on the surface of the Earth is the force acting on the unit north pole kept at that place. Okay. So these are the three elements, three magnetic elements of the Earth. Okay. So is the magnetic field strength maximum at the poles? Answer is no. There are one or two more places on the Earth which are called magnetic foci. So there the magnetic field strength is more. So that is why the Earth's magnetism is not straightforward magnetism, it is complicated sort of. Okay. But for us this much is sufficient, that magnetic field strength definition. In some places they call this third element, they don't call this one. The third element they don't call the total field strength. The third element they call it as a horizontal component of this. Okay, so that is what we are going to look at. So after finishing the three elements, let us say this is the Earth, and let us say at this point on the surface of the Earth, okay, you have the direction of the Earth's magnetic field like this. Okay, so the length of this vector, okay, is showing the magnitude, and the direction is of course showing the direction. Okay, so this is the vector representing at the direction as well as the magnitude at some point on the surface of the Earth. And let us say this is the horizontal. This is what? This is horizontal. And this angle is theta. So what will be theta? Theta is the angle of dip. So can we, and let us say this total field strength is, let us say F. So can we resolve this F into horizontal component, vertical component? Yes. So the horizontal component will go like this and vertical component will come like this, correct? So this total field strength at this point on the surface of the earth, we have resolved into two mutually perpendicular direction. One is the horizontal component, one is the vertical component. Right? So if I zoom this thing here and show it separately here for the sake of clarity, let us say this is the total field strength F at any point on the surface of the earth. And this is the horizontal and this is the vertical. So this we can say this is the horizontal component and this is the vertical component. Okay. So this is horizontal component and this is the vertical component. This is vertical component, this is the horizontal component of F. And this is your angle of dip theta. So this horizontal component is denoted by letter H. And this vertical component is always denoted by letter Z. This H and Z are the fixed letters. You cannot make it X and Y or A and B. H, it has to be used, the letter only H has to be used, letter Z has to be used. So all of you know the resolving. So what will be H? H will be equal to F cos theta. Right? Or if you take cos theta will be equal to H upon F. So F will be equal to H will be equal to F cos theta. And what will be Z? Z will be equal to F sin theta. Right? So this angle is theta. This angle will also be theta. So sin theta will be equal to Z upon F. So Z will be equal to F sin theta. Okay, so these are the two components. But in some books, this H is known as the third component, third magnetic element of the Earth. But this is the most important one. Okay, so what is this H? H is horizontal component of Earth's magnetic field. So H is the horizontal component of the Earth's magnetic field. This is the horizontal component. And what is Z? Z is, you can say, vertical component of Earth's magnetic field. So what is the thing which is making the magnetic compass and magnetic compass? It is H. You remember when we did the principle of magnetic compass, that time what we had done? That time we had shown one needle like this, and on that needle, that force was like acting like this, force was acting like this, and there was a field which was creating this force, MH, and that field we had called it H. What is that H? This is this H. Because your needle, magnetic compass needle, is rotating in the horizontal direction of horizontal plane or vertical plane or any oblique plane. Hello.
Horizontal.
Horizontal plane. So magnetic compass needle is constrained to rotate in the horizontal plane. So in the horizontal plane, which force will be acting on the magnetic compass needle? H or Z or F?
H.
H. So that is why it is this force H which makes the magnetic compass a magnetic compass. This is the most important force. That is why in some books this is shown as a third component, because the Z is not doing anything. It is only creating problems. That is trying to pull the magnetic compass down. So that is not helping in any way. Okay. So that is why this force H is also called, this force H is also known as directive force. Because this is the force which is giving the directional property to the compass. So that is why it is also known as directive force. Okay. So the value of Z at different places of the world is also tabulated and available. Okay. Actually, if you know F and you know theta, so then you can find out H, you can find out Z. Okay. So you can see H is equal to F cos theta, Z is equal to F sin theta. So what will be tan theta if you say tan theta will be equal to, because if this is Z, this will also be Z, ये भी Z होगा. So tan theta will be equal to Z upon H. What will be the value of F? H square plus Z square. So if you know two things, the third balance two can be found out. Okay. If you know theta and H, okay, you can find out F, and once you can find out F, you can find out Z. So in which direction H will be acting? In which direction H is acting? H is always acting towards north. Because ये जो डायरेक्शन जो है फील्ड का, ये इसको अगर यहाँ पे एंगल और डिप को जीरो कर दें, तो ये निडल किस डायरेक्शन में पॉइंट करेगी? नॉर्थ की डायरेक्शन में ना, मैट्रिक नॉर्थ की डायरेक्शन में. हेलो.
Sir, but if you are in the southern hemisphere, won't it point in the other direction, sir?
No, we'll go to the southern hemisphere later. But northern hemisphere, you have understood?
Yes, sir.
So H is always pointing in the direction of the north. Irrespective of the place on the surface of the earth, H is always, because if H was not pointing towards the north all the time, then your magnetic compass will be pointing in different directions and different places, because it is this force H. कौन सा फोर्स था जो उसको खींच के नॉर्थ साउथ बनाता है? H. So this force is H is always acting towards north. Because of that, magnetic compass needle, okay, which was lying in this direction, it comes in this direction. If this force is acting in this direction, then this magnetic compass needle will go and point in this direction. No? Hello. So the direction of H is always and always and always towards magnetic north. Okay. Now, you can see Z. The Z is acting vertically downward in the southern hemisphere. What will happen in the northern hemisphere? Let us say now your blue end of the needle is pointing. Let us say, let us show in the same way. Let us say that needle is pointing in this direction. So which end of the needle is pointing in this direction? It is this blue end of the needle which is pointing in this direction. Okay, and this is the horizontal end at place. So this is your angle of depth. And what about the red end of the needle? Red end of the needle is pointing in this direction. That means north end. Okay. तो इसका अगर आप कंपोनेंट लोगे हॉरिजॉन्टल कंपोनेंट, तो हॉरिजॉन्टल कंपोनेंट H will be this, and what will be the vertical component? Vertical component Z will be this, right? Because direction of the field is taken as this direction. So when you take a component of this one, the horizontal component will go like this, and vertical component will go like this. So this is also direction towards north only. Understand? Hello. Only thing is that in the northern hemisphere, the Z is acting vertically downward, and the southern hemisphere, the Z is acting vertically upward. Understood? Hello. So direction of H in the northern hemisphere, or whether it is in the southern hemisphere, the H is always acting towards north. Okay.
Okay, sir. Okay.
And so H is always acting towards north. Z is acting vertically downward in the northern hemisphere, and Z is acting vertically upward in the southern hemisphere. Okay. So we can say in northern hemisphere, Z is acting vertically downward. In southern hemisphere, Z is acting vertically upward. But what is the direction of H? Direction of H is always upward. At any point on the surface of the Earth, northern hemisphere or southern hemisphere. That is this H, force H, which is responsible for bringing the magnetic compass needle to point towards northerly direction. Then the next thing is, as you can see, H is equal to F cos theta. Okay, so if I write here, let's say, let's remove this. If I write, let us say H is equal to F cos theta. So what is the value of H will be maximum where? What is the value of theta at equator? 0. And cos 0 is 1, which is the maximum value of cos. So can we say H will be maximum at equator? Hello?
Yes, sir.
Because here the value of theta at equator is 0. So cos 0 is 1, which is the maximum value of cos. When we go to the poles, okay, at poles, what will happen? Theta will become how much? 90. Cos 90 is how much? 0. So H is what? H is 0 at poles. Okay. So value of H is maximum somewhere near the equator, and value of H is 0 at poles. Because the theta becomes 90. So anything which is vertical, when the direction of the magnetic field at the poles, it is vertical. So anything which is vertical, uska horizontal component kya hoga? 0. That is another way you can understand. So as we go from the equator towards the pole, the value of H, as we are going from equator towards the pole, value of H is coming down, correct? Because cos theta is 0 here, 1 here, and cos theta is 0 here. So value of cos theta will continue to reduce. Cos theta का graph कैसे आता है? Between 0 to 90, it comes like this. This is 0, this is 90, correct?
Yes, sir.
Okay, so that means the directive force is becoming weak as we go to the higher latitude. Can we say that?
Yes, sir.
So that is why the magnetic compass is not so reliable in the higher latitude. Magnetic compass is not so reliable in the higher latitude because the H becomes weak in the higher latitude, and the force which is responsible for making the magnetic compass, or the force which is acting on the magnetic compass needle to make it align in the north-south direction, that force itself becomes weak. That is why magnetic compass is not so reliable in high latitudes. Okay.
Yes, sir.
So somebody will teach you the high latitude navigation. I don't know whether it is in phase 2 or there, or maybe ASM it is definitely there. So there, this will be one of the points which you will see come across. Then what will happen to the value of Z? Z is equal to F sin theta. F sin theta. So what is the value of Z at equator? 0. For sin theta is 0. Sin 0 is 0. And what will be Z at poles? Maximum. So the value of Z increases when we go from equator towards the pole. From 0 to maximum. And value of H reduces when we go from equator towards the pole. But if Z is of no use, it is becoming maximum, but it is of no use. So it is basically the H which is having a larger impact because of the change. What impact it is having, that we'll see later on. So is this all this illustration understood?
Yes, sir.
This is about the Earth's magnetic field. Now we will go to the ship's magnetic field. Or we call it ship's magnetism. Ship's magnetism. So no, if a ship is made of wood, then of course there'll be no problem. Then your magnetic compass needle will be pointing towards the magnetic north. But because we are working on the ship which is made of steel, and anything which is made of steel will have some induced magnetism in the structure. So because of that, what we see that magnetic compass needle is not pointing towards the magnetic north. It is pointing in some other direction that we call it compass north. And then that angle by which it is deflected from the magnetic north, that we call it deviation. Okay, the ship's magnetism is, what is the cause of the ship's magnetism? 99.9% of the cause of the ship's magnetism is the Earth's magnetism. It is the Earth's magnetism which is inducing the magnetism in the ship's structure, okay, which in turn is creating a field at the magnetic compass position, which is deflecting the magnetic compass needle away from the magnetic north in some other direction, causing a deflection of the magnetic compass needle and causing a something which is called deviation. Okay, so ship's magnetism can be divided into two parts. One is called hard iron, and the other one is called soft iron. Hard iron magnetism and soft iron. This also can be called permanent. This can be called temporary. So what is hard iron? Hard iron is iron. So let us say first, let us talk a little bit about 1 minute about induction. Let us say there is a magnetic field. I think we have already discussed this. Okay. So let us say there is a magnetic field in which I keep a material which is capable of becoming a magnet. So it will, because of the induction, what will happen? That this magnet will become, this material will become magnet. Okay, so that is called induced magnetism. Okay. So what is the inducing field? This is the inducing field, and because of this inducing field, there is an induction here. So what will happen? जहाँ पे enter होता है, that will become what? That will become blue. I think we had discussed this earlier. That end will become blue, and then from where it is exiting, that end will become red. यहाँ से magnetic compass and this inducing field is entering, so this point will become your blue end, or you can say south. And जहाँ से निकल हो रहा है वहाँ पे वो क्या बन जाएगा? Red, or you can say north. Because what happens? Because अगर ये red or blue बनेगा तो within the magnetic compass the field is going in this direction from red to blue. So always the induction, whenever it is happening, it is always trying to oppose the cause which is causing it. So the cause is in this direction, so the induction in such a way so that it is opposing. Okay. So similarly, when the ship is being built, okay, that time the ship is steel is receiving the induction from the Earth's magnetic field in the same manner as I have told you. So there'll be blue poles, there'll be red poles created. So in the case of hard iron, what happens? Hard iron is that iron which, if it is kept in a magnetic field, inducing field, it will not acquire magnetism very fast. It will take some time for it to magnetize. But once this type of iron acquires the magnetism, once the magnetism is induced, then it will retain the magnetism for a very long period of time. So hard iron is that iron that is difficult to magnetize and difficult to lose magnetism if the inducing field is removed. In contrast to that, what is soft iron? Soft iron is that iron, if it is kept in the field, it will acquire magnetism very fast, and induction will be very fast. But as soon as we remove the inducing field, also it will lose the magnetism very fast. You can say easy to magnetize and easy to demagnetize also. But there is nothing like perfect hard iron, perfect soft iron. So the iron which is predominantly acting as a hard iron, we call it hard iron. The iron which is called predominantly acting as a soft iron, we call it soft iron. Okay. So what we are going to look at is first is the hard iron magnetism. Hard iron magnetism is responsible for about 75 to 80% of the deviation what we see on the ship. Hard iron magnetism. So now we are on the topic of ship's magnetism. What happened? This hard iron magnetism is acquired by the ship mostly at the time of new building, when the ship is being newly built. So that time the steel is raw. Steel has still not received the induction because steel is coming from the factory. Then at a time of new building, the ship is lying in the same direction for a long period of time. When the ship is being newly built, the ship is lying in the same direction for a long period of time. Then the Earth's magnetic field is passing through that ship, creating blue pole and red pole. How? Let us take a simple example. Let us say this is a ship. Okay, so this is the forward, this is the aft. Let us say the ship is being built and the Earth's magnetic field is coming like this, is coming in this direction. And of course, going out from here. So the Earth's magnetic ship is being built heading in this direction, and the Earth's magnetic field is going in this direction. What will happen? Because the Earth's magnetic field is entering from here, so here what will become? Here what will become is blue poles. So what it will require here? It will be on. Okay, so all this will become blue pole. And down below, यहाँ से enter वहाँ पे
क्या
blue pole. Yes.
सर कौन से बोले हो?
What?
अभी कितना निकाला? डॉट क्या है सर? अभी जो डॉट निकाला ये पोल बोले ना आप कुछ तो.
I thought the way you were talking, I thought you were talking to somebody else. The end from where? अभी आपको inducing field का बताया था ना, जब the side from where the inducing field is entering, that becomes blue pole, and the जहाँ से वो exit होता है, that becomes red pole.
Okay,
Just now I told you that this is the inducing field. Okay, in this inducing field, if I keep a material like this, let us say I keep a iron bar like this, so this end will become blue and this will become red by magnetic induction. So you can say the deck of the ship is having blue pole and the keel of the ship is having red pole. Right?
Okay.
So then what happens? Let us say this is the position of the magnetic compass. What is this black dot I am showing? This is your position of magnetic compass. So because of this red and blue pole, there will be a force acting at the magnetic compass. So the force may be acting in this direction, in this direction. So there will be many directions where this force is acting because of this red and blue pole. So these red and blue poles, when it is created, they in turn will be causing a field at the magnetic compass position. Correct? तो पहले क्या किया? अर्थ ने शिप के स्ट्रक्चर में मैग्नेटिज्म इंड्यूस किया और ये ब्लू पोल एंड रेड पोल बना. फिर आफ्टर दैट दिस रेड एंड ब्लू पोल व्हाट दे आर डूइंग? They are creating a field at the magnetic compass position. Okay. So when this field is acting in this direction, so this field will have a final resultant. Oh, okay, let us say that we'll see in the other diagram. So these blue poles and red poles, are they temporary poles or they will become permanent? They will become sort of permanent poles. And throughout the life of the ship, these blue poles and red poles are going to remain with only 5% reduction in a period of 25 years. So that is, you can say, hardly any reduction. We can call it that once these blue poles and red poles have been acquired by the ship at the time of new building, then these blue poles and red poles will be retained by the ship and will retain their position throughout the life of the ship. Understood? So it is like
Yes,
become
sir.
like a permanent magnet. Okay. Then we can show another diagram. So let us say the ship is being built like this. Now here what is happening, the direction of the Earth's magnetic field is coming in this direction. And it is going in this direction. Now what will happen? Here what will happen? This will become a blue pole. Okay, so this will become all your blue pole. Blue means south. And here will become what? Red pole. So there will be numerous red poles and blue poles. And this is your magnetic compass position. This is your magnetic compass position. So due to these red poles, somewhere on the higher side of the vessel on the deck, and blue poles located towards the keel, so the force is acting from always from red to blue. So at the magnetic compass position, due to this red and blue pole, the force is acting. Let us say one force is acting in this direction, one force is acting in this direction. So like numerous forces are acting because of this red and blue pole. But whatever the number of forces which are acting in this direction, these forces will have a final resultant. On one body, you can show thousands of forces, but all those 1,000 forces will have a final resultant or not?
Yes, sir.
Hello? Like if 30 people are pushing me from all the 4 directions, all from many directions, I will move in only one direction. So I will move in the direction of the resultant. So like many forces which are acting at the compass position in this direction, some are in this direction, some are in this direction, some are in this direction. So finally they will have a resultant. Okay. Let us say this is the resultant. This is the final resultant which is acting at the compass position due to all these red poles and blue poles. Okay. So let us call this as F. So actually F ऐसा कुछ नहीं है. This F I have just named it for the sake of teaching. What is F? Let us say what is F. F is the can say F is the permanent magnetic field. Permanent magnetic field. When we say field, field is direction as well as the magnitude. So F is the permanent magnetic field acting at compass position. And from where this permanent magnetic field has come? This permanent magnetic field has come because of the induction in the ship structure by the Earth's magnetism. So what is the cause? Earth's magnetism. Inducing field is what? Earth's magnetism. Earth's magnetism caused the magnetic induction in the ship's hull. The ship's hull, the induction which was caused, that created a force at the magnetic compass position. That magnetic compass position, the final resultant is this F. So F is the permanent magnetic field acting at the compass position. Okay. Any doubt? And this force F will not change throughout the life of the ship. It will remain same. It is not going to change. Once the vessel has acquired this high diameter magnetism at a time of new building, the direction and magnitude is not going to change. It is thought it has become a permanent magnet. So we can call it permanent magnetic field. We can add one more line here. Sorry, one more word. It is the ship's permanent magnetic field acting under compass position. Now, what we have to do is that this force F, can we measure? No. This force F, can we correct? No. So now we have to resolve this force F into such a way, so that we are able to find out the deviation caused by this force, and also we can correct these forces, or we can correct the deviation caused by these forces. So if we know only F acting at the compass position, it is of no use, because we cannot do anything with this information. But if we resolve this force into horizontal and vertical components, then those horizontal and vertical components we can calculate, or at least we can calculate a deviation caused by those horizontal and vertical components, and then we can correct those horizontal and vertical components. Okay, so now we are going to resolve this force F. So this force is F is acting in what direction? This force F is acting in any direction. It could be acting in any direction. Okay, in any oblique direction. So if I show that, let us say this is a duster. Okay, and at this duster, let us say this corner, what I'm showing, this is the magnetic compass position. Ye wala corner jo hai, this is the magnetic compass position, and this force F is acting in this direction. So are you able to see that in which direction this force is acting? Hello?
Yes, sir.
So where my thumb is what? Thumb is the position of the magnetic compass. At the magnetic compass position, the force is acting in this direction. And what is this? This is the ship. So this is the forward of the ship, and this is the aft of the ship. This is the starboard side of the ship, and this is the port side of the ship. Okay. So at the magnetic compass position, this force is acting. You can say this is not acting in the forward direction or athwartship direction. It is acting in some other direction. So this force which is acting, this is the F force, what I had showed in the diagram. So this force can be resolved into horizontal component like this, and vertical component like this. Any force can be resolved into two mutually perpendicular directions. One will become F for F. One will be the cosine component, one will be the sine component. So this total force which is acting, magnetic field acting at the compass position, we can resolve into horizontal component and vertical component. Correct? Is this part understood?
Yes, sir.
Okay. So horizontal component is like this. So horizontal component at the compass position is like this. This is the horizontal component, and this is the vertical component. Is this understood? तभी
Yes,
F को हमने रिप्लेस कर दिया हॉरिजॉन्टल और वर्टिकल कंपोनेंट से. अभी वर्टिकल कंपोनेंट तो हमने छोड़ दिया, वो हमको एक कंपोनेंट मिल गया, ये वाला कंपोनेंट छोड़ दिया. अभी जो हॉरिजॉन्टल कंपोनेंट है, इसको वी कैन फर्दर डिवाइड इनटू टू कंपोनेंट्स. Which component? One component we can call it fore and aft component, and one we can call it athwartship component. ये वाला कंपोनेंट जो था, this is the horizontal component. तो इस ये वाले कंपोनेंट को हमने fore and aft component and athwartship component we can divide. Further we can divide into two mutually perpendicular directions. Understood?
Yes, sir.
So remember that first what we did, the total force we resolved into horizontal component and vertical component. Then this horizontal component further we have resolved into two mutually perpendicular directions. So one becomes the fore and aft component like this, and one becomes the athwartship component like this. So this is the athwartship component. Okay, this is the athwartship component,
and this one we can call it, say, let us say, difficult to show. Okay, so let us say this becomes your horizontal component. So this is your 4.5 component, and this is your authorship component. So basically, this force F we have resolved into 3 components. So this forward component is known as 4.5 horizontal component. This authorship component is known as authorship horizontal component, and one was the vertical component. तो एक component कैसा हुआ, एक component ऐसे हुआ, दूसरा component कैसा हुआ ऐसे, and तीसरा component कैसे है ऐसे. You can say x axis, y axis, z axis as you can see. ठीक है ना? जैसे if you see that, let us say okay, so let us say this force is acting in this direction. So you can resolve this into this component and this component and this component, correct? Hello? So this becomes your authorship component, this becomes your 4.5 component, and this becomes your vertical component. Okay? Hello?
Yes, sir.
Yes, sir.
So this total force acting, total magnetic field acting at the compass position, we have resolved into 3 mutually perpendicular directions. Okay. So one was this component, which is 4.5 horizontal. This is authorship horizontal, and this is vertical component. What is this? This is the 4.5 horizontal component. This is what authorship horizontal component, and this is called vertical component. This 4.5 horizontal component is called force P. Authorship horizontal component is called force Q, and vertical component is called force R. So this total force we have resolved into 3 mutually perpendicular directions, calling 4.5 horizontal component as P, authorship horizontal component as Q, and vertical component as R. Okay. So what is this force P? If we write what is force P is fore and aft horizontal component of ship's permanent magnetic field acting at compass position. P is 4.5 horizontal component of ship's permanent magnetic field acting at the compass position. So this was the permanent magnetic field acting at the compass position. Uska 4.5 horizontal component is force P. What is force Q? Force Q is authorship horizontal component of uske baage ka same. So what is Q? Q is the authorship horizontal component of ship's permanent magnetic field acting at the compass position. And what is force R? R is the vertical component of same ship's permanent magnetic field acting at the compass position. So P, Q, and R are the components of the ship's permanent magnetic field acting at the compass position. And 70-80% of the deviation is caused by what you see on the ship is called by this force P and Q. If you don't correct the magnetic compass, what will be the amount of deviation? Amount of deviation could be 40 degrees. By correcting the magnetic compass, you are bringing it down to 4-5 degrees. That is what the value is what you see in the deviation card. But अगर आप सब corrector magnet को निकाल देंगे तो क्या होगा? Your deviation will become 40 degrees. So then your true course is 210 and पता चला compass force is coming out to be 250, 255. That is too much. Okay.
Sir, can you please tell again what is value Q?
Q is the horizontal athwartship horizontal component.
Okay, sir.
Athwartship horizontal component of ship's magnetic field acting at the compass position. So the total field which was acting at the compass position first be resolved into horizontal and vertical component. That horizontal component again we divided into two components. One was the fore and aft and one was the athwartship. So athwartship component of that fore and aft horizontal athwartship component of that horizontal component is called the force Q. Okay.
Yes, sir.
Okay. So there is a sign convention which is used for this force P, Q, and R. Force P is called for positive if it is acting towards bow. And force Q is called negative if it is acting towards stern. Force Q is called positive if it is acting towards starboard. And force Q is called negative if it is acting towards port. Force R is called positive if it is acting towards vertically downward. And force R is called negative if it is acting vertically upward. Okay. चलो ठीक है, then we will continue in the next class.
Thank you, sir.
Thank you, sir.